Okay, go ahead and open up QGIS and we'll look at the data. Alright, so the first thing I'm going to do, just like I did last time, is save my project. And I'm going to save my project right where I want it to navigate to everything. And so it looks like I've already saved something there. I'll just overwrite this file here. And that's good. So now my project home navigates right to all my data folders. So we're in Maine. So let's just pull up something in Maine that we can look at. We'll pull up the town boundaries, all the town boundaries here, and go ahead and choose this Maine here. So do that. And so this is a town boundaries file. We're not looking at the whole state of Maine. We're looking at one watershed. So let's see. We've got a boundary called study area, which we can bring in. So it looks like we're looking at this section of the coast. I'll zoom into there. A lot of times with my study areas, I like to make them hollow so I can see inside and have a boundary. So I'm going to double click that under my symbology. Q symbology can be a little cumbersome, but once you get used to it, it's fine. So I want to make it hollow, which means I actually need to go to, it has a fill, but then actually it's being symbolized with a simple fill. There's other settings you can do here, obviously, but under the simple fill, which is this one, we're going to go to solid, no brush, and then I'm going to change the stroke color, which is the outside, to, let's make it a red, so it's really obvious and a little thicker. So I'm going to say apply, and so now I can see my study area is nicely kind of outlined. I say okay. Okay, so we know this is a watershed or some kind of watershed. Let's look at the hydrography then in that case to see what we're looking at. There's a lot of information here. I think to begin with, maybe we could just throw in some of the actual water to see what the kind of skeleton of the landscape looks like with the water. The National Hydrography data set is kind of the gold standard for water data in the United States. It has different problems and things like that, but it's a great data set. There's a medium resolution, a high resolution, and then a high resolution plus, which I'm sure someday you'll experience. But this is the medium because we're looking at a regional scale here, right? We're not making maps that are, this whole map is going to be, the product is going to be something that's for multiple sets of land trusts that are working collaboratively in a large watershed. So let's bring in area, and let's bring in water body and flow line. And it's kind of hard to look at right now because it's all random colors. So maybe we can change them blue. In Q, one of the fast things you can do is you can right click a layer, go to styles, and then you can kind of just choose on the color wheel, you know, something a little better if that's what you want to look at. And I want to get rid of that stroke on the edge of it too, so I can go right to edit symbol here. I don't have to go into properties. And same thing, simple fill. This time I'm going to get rid of the stroke style. Just go like that and say no pen. Okay, and so it creates this borderless hydrography. And now if instead of doing that whole exercise again to get the area to be the same symbology, which is this ocean, I can actually right click here and go styles, copy symbol, because I want it to look exactly the same. And then I can go here, right click or control click on a Mac and say paste symbol. And so now I've got some blue water. You might be wondering, why is there water body and hydro area? And there's a whole bunch of different reasons for how they categorize things. Maine is interesting though because it has, you know, some of the, you'd think, okay, water body, that must be fresh water. Those are places that there are lakes and things like that. There's some intertidal areas as well though, right? Like we know that this is mostly salt water, but it's being symbolized as if it's part of a of kind of the water body thing. Whereas Merry Meeting Bay and the Kennebec River and the Androscoggin River are being symbolized as the NHD area. And I'm sure there's a bunch of literature that you could read about why they do that. So the hydro flow lines, these are also medium resolution. You can kind of, if you're interested, you can take your eyedropper tool and go kind of look at the names of certain rivers. There's the Pemaquid River, Back Brook. This is the Madomic River. But we're just going to use the hydrography data for symbology in our maps if we're doing a print map. We're not going to use it for analysis. But so this should give you kind of a good idea that we're working on the coast of Maine. It's a coastal flowage here, so it's not actually that huge of an area. The Kennebec watershed, for instance, is probably, I think it takes up about a third of the state for just the Kennebec River and all of its tributaries. This coastal kind of flowage is not, it's much smaller, and there's kind of a bunch of them. There's the biggest watersheds are, I guess I could pull it up here and show you. Here we go. So here's some watersheds for Maine. We're in this coastal zone here, which is kind of this purple situation where they're all just flowing straight to the ocean. This is the Androscoggin, which is also flowing to the ocean, but it includes a much bigger region. I think that's that's the Kennebec. This is the Penobscot, this is the Kennebec, and then this is the Androscoggin, and those are the kind of biggest watersheds for Maine. And this watershed up here is the St. John. So it actually flows north, and it flows into Canada and kind of comes out in the Bay of Fundy. So anyway, just for context, this is what we're looking at. There are a lot of land trusts in this area because there's a lot of people. It has that dense parcel pattern that we talked about. And so at one point there was a land trust almost for every watershed. And so we'll check that out right now. And I just said every watershed, and I think it might be confusing because we were looking at the big watersheds, but watersheds kind of nestle, right? There's smaller watersheds within larger watersheds. So that's what this mid-coast watersheds is going to show us, is a different category of watersheds within our study area. So this is all kind of one watershed of things that flow kind of to the ocean. But then there are these smaller watersheds, and these are the subject areas that the land trusts care about. So let's bring in the land trust file, or the conserved lands file, and I'm going to bring in this conserved lands with attributes. And so these are all of the parcels that the state of Maine believes are conserved. And I speak that way, believes are conserved, because I've worked with a lot of these land trusts, and it's not complete, right? There's a lot more information that you could find on, for instance, there's one land trust in my home area here that there are more conservation easements and things like that are not being visualized in this conserved lands database. But the reason for that is that, for a statewide data set, you have to kind of imagine that they're compiling, kind of like Humpty Dumpty, all of these different providers that are reporting what parcels are conserved. And so, it's a massive job for an entire state to try to compile a data set like that. So let's categorize this conserved lands file so that we can look at some of the data. A lot of times before I do any symbology, I like to look at the attribute table just to see what's in there. And if you look at this, you'll kind of see a few different fields. It looks like we have some kind of object ID, which is a unique ID, I'm imagining, for every parcel. Project, which is like the name of the preserve. Often many preserves have multiple parcels that comprise them, and so the project is usually, what that means is the name of the entire kind of area. Conservation type, we can talk more about this in discussion, but in general, it's usually there's fee and easement are kind of the two big ones. Fee means that someone owns it and pays property taxes on it. And easement is something where a property owner has a piece of their land that they would like to not pay taxes on, usually. There's a whole bunch of different types of things you can do, but the easement is they agree not to use it for development, and therefore they get kind of a break on their taxes. And there's some other categories, but fee and easement are kind of the two conservation types that we're going to see most often here. Holder name. So this is kind of important. This is what we're going to symbolize in our symbology. This is the name of the organization that either holds the easement, right, or owns it. And so, for instance, an easement held by the Madomic Valley Land Trust may indeed actually be owned by someone else, but the easement holder is kind of the land trust that says, yes, we legally know and will manage this land that you're not developing. And then the holder type tells us, is it a state agency, is it a town or municipal agency, is it a private entity, or is it, I think there's probably a federal, well, maybe there's no federal in here. But all land trusts are kind of considered private organizations. And so, most of them are some form of nonprofit, but they're still private entities. They're not public entities. And then we have an acquisition date, which is always interesting to see how long these things have been preserved, and something about public access and gap status, which I think we'd have to ask a professional conservationist what that means. I'm not exactly sure. Maybe Bill knows. Okay, so let's categorize it I want to see by holder name. Let's just see what the patterns are here. So we go categorized by hold name, classify, and so we're going to get a whole bunch of different folks here. Hit apply. Okay. And you can kind of start to see how there's a little bit of regionality with it, right? We've got, like right in here, this is all this kind of tan is the Madomic Valley Land Trust. And we've got in blue here, I think that's the Pemaquid Watershed Association. We've got the Kennebec Estuary Land Trust. So they're regional, and it's because they're local organizations, right? They derive their revenue from member donations and different things like that. And so they're very much based on some form of the will of the local people that care about conservation to volunteer and contribute and kind of and acquire land and easements and preserve it for occasionally for public use, but also for the ecological assets that might be there. And that's an important distinction. I think I've actually been talking about conservation very much in relation to recreation, or how humans expect to use the landscape, because I've been stressing how subjective it can be. There's also this idea, though, of course, that conservation should be to preserve ecological assets. And in Maine, there's this great organization. It's called Beginning with Habitat. And Beginning with Habitat is, it's their kind of purview to map the state and record its ecological assets for land trusts, for other nonprofit groups that want to kind of conserve land or have an environmental goal. So I would encourage you to go and look at some of these maps, and what they do is they will record different types of habitat, different wetlands. They have a whole series of maps that they publish. They also have what are called Co-Occurrence Maps, which are interesting. Let me just see if we can just pick a random one here. Map 3, Map 7, Co-Occurrence. So they have a set symbology and a set series, but then they also they do this co-occurrence, which shows the value of the ecological kind of categories as they stack up on each other. And so later this week we'll be talking about kind of making some of those types of maps. But so anyway, ecological assets, that's in some cases the real driving force behind conservation. Recreation to many people is seen as very secondary. But so our imaginary question then is, all of these land trusts consider themselves a part of one eco-community or a connected eco-community, and we're using the watershed as kind of this imaginary boundary for how they're connected. And they'd like to create a visual that shows what are the ecological assets for each watershed, each of these sub-watersheds, and is there a way we can kind of summarize by watershed what those ecological assets are, how many acres there are per watershed of each type of asset, and what are the percentages, right? So the goal being, are there certain watersheds that we should collaboratively focus our conservation efforts toward? So to do that, let's actually look at some of those. I'm going to take off this town boundaries and the flow lines, which are kind of messy, and let's just look at some of those ecological assets. So if you go to habitat, you'll find H underscore deer wintering area, H underscore inland wader waterfowl, H underscore tidal wader waterfowl. And these are just 3 basic habitat categories. So we'll bring them in. And they're kind of coarse, but they're just digitized polygons that are based on a set of criteria for where a professional ecologist has told us to expect there to be deer wintering areas, or where there are inland wader birds and waterfowl, or there's tidal. And so these are kind of the best thing we can kind of find for the state of Maine for some basic habitat categories that we could consider ecological assets. And of course, one of the most important and obvious ecological assets would be wetlands. And so let's take a look at some of the wetlands data. We've got a couple different files here for wetlands. We've got wetland by type, and this is kind of an intense file. This is called this is from the National Wetlands Inventory, which is similar to how the NHD is the gold standard for hydrography for the United States. The National Wetlands Inventory is kind of more or less the gold standard for the wetlands data for the whole country. It has various levels of accuracy depending on what part of the country you're in, but it's great because it does actually categorize wetland by forested and freshwater emergent, and a couple categories we're not seeing here, which are marine, estuary, riverine, deep water, that kind of thing. For the purposes of our lab, because we're going to be summarizing by watershed, the geometry of these watersheds is kind of heavy. It's a lot to try to run through a program. And so we're going to be using this wetland basic area, which is a little wonky, but it's not bad. It kind of generalizes the wetland areas based on kind of freshwater emergent, I think, is the primary category. And it starts with the National Wetlands Inventory, but it's a much more manageable file to push through some tools. So what are we supposed to do? We're supposed to come up with an acreage estimate for each of these, which seems like kind of an intense workflow, right? We're going to try to get by watershed some summary of how many acres of wetlands in a percentage, how many acres of each type of habitat as a percentage. And I think already you're starting to think, oh my gosh, this is going to be a repetitive exercise. And I think for the rest of the video, before we start the analysis, I want to just talk about workflow efficiency, right? So what do I mean by workflow efficiency? Well, what I mean is we know what the answer is, right? We know what we're trying to arrive at. We're trying to arrive at a mid-coast watershed shapefile where, in addition to the attributes it already has, it has several additional attributes. Let's say it has 8 additional attributes. So for each watershed, we want to see acreage and percentage of these categories that overlap in these watersheds. And then we also probably want to have the area in acres of each watershed. And so it seems like, okay, well, how would we do this using the tools that we've used in the past? You might think, well, we could just intersect each of these individually and then kind of create some type of area calculation with those resulting files, and then maybe we could kind of join it back. And so I'm going to pull up a diagram of a way to think about these types of workflows, because also ultimately I think GIS a lot of the time seems like it should be about finding the answer, but a lot of times we kind of know the answer, and it's more about how to find the best way to arrive at the answer. So here's kind of my over conceptual example of what I'm talking about. In this very simple kind of arithmetic example, let's just pretend that the answer is 24. in the same way, let's assume that these are pieces of data, and then these are tools, right? We have the plus tool, the multiplication tool, the division tool, a factorial tool, and a subtraction tool. The most obvious way to get there would just be to take one piece of data and add it a certain number of times to arrive at the answer of 24, right? We all know this is probably the least efficient way to do this answer, but it's straightforward, right? Maybe we're only comfortable with that piece of data and we're only comfortable with that tool, and this is very repeatable. So we think, okay, well, we just do that. The problem with workflows that do this type of thing is that every time you use a tool, you're introducing a chance that the error will kind of enter the analysis. You know, even even when I was writing this out, I had to kind of keep track of how many 2s I was adding to make sure it added up to 24, right? So you might say, okay, well, a little bit better is, you know, we could do 3s and add them 8 times, and so we've increased the efficiency of the workflow. But it's still pretty ridiculous. We're only using one tool, and we're using a piece of data not very well. Okay, 6 4 times, that's a little better. But I think if we use some of these other tools, we can kind of get the workflow to be even more efficient. And let me just zoom out here. So this is kind of where we start to be more creative. We say, well, we can't just simply multiply, you know, there's no 4. We don't have a 4 data set, so we can't go 6 times 4 equals 24. But if we took 6 and subtracted 2 and then multiplied by 3, okay, well, that's 3 pieces of data instead of 4, and we're only using 2 tools. We're using the subtraction tool and the multiplication tool, right? So we've moved from 4 instances of data and 3 tools to 3 instances of data and 2 tools. But then, you know, occasionally you get lucky, and there's a tool that kind of really helps tighten things up. And so, you know, in this instance, we could use 2 instances of data with one tool to subtract them, and then another tool, and then this is kind of the most efficient solution for finding the answer, which is 24. So it's kind of a backwards way of talking about it, but I think it's helpful to remember that none of these answers are wrong, but some of them are more efficient, right? And sometimes, even though something is the most efficient, let's say that this is the most efficient way to get to 24, if the tool, like a factorial symbol, right, 4 times 3 times 2 times 1, let's say this is a complicated GIS tool. If our client doesn't understand that tool, then sometimes it's worth it to have a workflow that is just a little more redundant, so that we can kind of explain what we've done to our client who might not be an expert, right? A lot of times I will intentionally choose something like this, right? 6 times 2 times 2 in the GIS world, maybe a whole series of intersects or something like that, because the client is going to understand one tool and like maybe 2 pieces of data, whereas this is 3 pieces of data and 2 tools, and it's a lot more explanation. So anyway, I think using this as kind of a framework for understanding what we're talking about, we can go down to kind of what we're doing with the GIS now. If we were going to try to solve this problem the way we've described already, we would take each piece of data, we might intersect them individually with the watersheds and kind of create different resulting files. And then we would probably dissolve those files, because if you can kind of imagine, if you were to take this inland wader waterfowl or any one of them, each one of these objects is going to be separate. It's going to intersect separately. And so we really just want one reporting unit for each watershed. So when we intersect, we would have to dissolve, so that instead of getting an area measurement for each one of these per watershed, we're getting one measurement as a multi-part figure for each watershed. And I can show you what I mean by multi-part figure in the next video, if you're not sure what that means. But then of course, you know, we're creating all these files, and maybe we're doing a dissolve, and then we calculate by area, and then we do a join. Occasionally, with workflows like this, you can do what's called batch processing, where if they're very, very similar types of files, and you can even numerate them, go 1, 2, 3, 4, 5, 6. If you put them all in a folder, you can tell Q to look into a folder and run the same tool the exact same way a certain number of times. Or you could build a model in which you have inputs and outputs and you set it all up and you hit go. I find that those types of workarounds for inefficient workflows are only good if the parameters are simple. There's a lot of parameterization with this workflow, and so I would just probably click this one out because it's not too many. And once I got into a rhythm, I could kind of keep track, and I would set up my own folders for it. I'm not sure that you would save much time by creating a model, because if something got messed up, you'd have to go into that model and fix it anyway. So one way to arrive at the watersheds with the summary that we're looking for. You might think, okay, well, I think I can get better. Maybe what if we use that self-intersect tool or some other similar thing that we used before to merge all of these files into one file and then do an intersect. And so here's another potential workflow. You could take all of the ecological assets, merge them into kind of all features, do an intersect or some kind of union with the watersheds. And then you're going to get a very messy file that you could calculate the area, and then you would probably need to take it into Excel to summarize how all of those different attributes interact. The problem with this is that you're going to have overlapping topologies, right? So you're going to have, if you just merge these files as they are right now, you would end up with places where, let's see if we can find an example. Yeah, places where there's many versions of things overlapping, right? You're going to have a place like this where there's not only a deer wintering area, but there's also a wetland, and there's also another kind of habitat. So when you make files that have overlapping topology, the tools, you really need to know the tools. Some tools will respect that overlapping topology and they'll run, but they'll create these topologically redundant products. So you would end up with actually 3 pancaked little intersected files that are, or not files, geographies that are stacked on top of each other. There are other tools that just won't run if they call it, that the geometry is bad or that the topology is bad, and they won't let you run it until you fix the topology. So I think that this workflow could be figured out, but it's likely to fail, and it's likely to be difficult to keep track of, because even if you successfully merge and then intersect or perform a union with the watersheds, the resulting file is going to be such a mess that it's probably going to take almost as much time as this would to figure out what's supposed to go where and how to come up with your area calculations. So lucky for us, there is a factorial, I'm using that term metaphorically. There is a kind of the exclamation point version of a tool. There's something called overlap analysis, which will just do exactly what we want. We're going to say we want the watersheds to be overlapped, and we're going to have all these inputs, and then it's going to automatically create a file in which the watershed geometry is maintained, and then these attributes, there will be columns that are added that tell us how much area and what percentage of area is covered by the inputs. So anyway, I think I'll leave it there, and then in the next video we're going to do the analysis for these watersheds, and we'll see where we go from there.